Good morning, everyone. I hope that you guys are having a good start to your day. It is Monday, the 18th. We've got about, let's see, we got 3 meetings this week. We got one next week, and then we got one after our Thanksgiving break, and then we'll have our exam, number 4, and then we'll have our final. So we have a total of 5 more class meetings. I am planning for next Monday to be an asynchronous meeting. Um, so that I will post the recording. I believe I'll do it before Monday morning, before our 10 a.m. meeting. So you guys have that as, so you have that and you can access it at your leisure. So that's what I'm planning for next Monday. But this week we've got all our kind of regularly scheduled stuff. And I think we'll go ahead and get cracking. Today, what we're going to be talking about is we're going to be talking about acids and bases. Last week, we were talking about solutions, and we kind of finished our discussion of solutions. But now we're going to get into like kind of the variation or how solutions can be different and unique from one another. So here, what we have is acids and bases. And these are kind of the most common terms that are used in chemistry and outside of chemistry and, in industrial processes as well, um, for basically describing solutions. So acids and bases and pH, that's what we're getting into today. Now, where we are, oh my gosh, we are almost done. We got acids and bases and oxidation and reduction this week, and then we're kind of done. Now, acids and bases, what comes to mind when you hear an acid or a base? Um, whenever I think of or hear an acid, um, especially acid and base, um, I always think about like movies. I always think about I think it was in the movie Die Hard 3 where they had some sort of acid that they were going to release into the water system and it was going to be bad. So I always think about it kind of in like I guess like a fictional realm. Follow up to that though, what I also think about is cleaning solutions. So as an example, there are some acids and bases that you probably are a little bit more familiar with than you might realize. Um, if you, for instance, like myself, take a vitamin C supplement, well, vitamin C is an acid known as ascorbic acid. Not all vitamins are acids. For instance, vitamin D is a lipid. Um, the cleaning solution acetic acid or sorry, the cleaning solution vinegar is acetic acid. Hydrochloric acid, HCl, not muriatic acid. Um, this is a um, this is sometimes what people use to adjust the pH of their pool or hot tub or something like that. Same thing goes with sodium hydroxide or NaOH. That is a base. Another base on here is NH3. So these three, HCl, vitamin C, and acetic acid are all acids, whereas sodium hydroxide and NH3 are both examples of bases. Now, clear all my drawings. What are some properties of acids and bases? Well, acids, uh, yesterday actually one of my kids was eating some of their Halloween candy and they had warheads. I don't know if anyone's ever had, or it's been a minute since you maybe had a warhead. But those are the ones that are like very tart. And that is an acid that you're tasting whenever you're experiencing it. And you're like, oh, this is so tart. This is so sour. Um, and so that would be an acid. I don't know exactly what acid it is, but that would be the kind of flavoring agent or product that you're tasting there. Acids from a kind of grand scale in a chemical setting or an industrial setting, they can dissolve metals. Some metals, not all metals. And of course, the strength of that acid matters. Um, it can react with a base to form water and salt. And then a base. What's a base? Well, base has a bitter taste to it. and it is going to feel kind of slippery. Like if you spill some base on your hand or have some base on your hand, it's going to feel like, oh, it's a very strange sensation. But in the event that you are in a lab setting, or maybe you're cleaning something, all of a sudden your fingers feel super slick next to one another, you should probably go and rinse your hands off because that's probably a base, and an untreated or an or kind of ignored base can lead to a base burn. And so you want to be thoughtful and cautious of that. And then last but not least, it's going to react with an acid to form water and salt. Now, these two items in the middle, I went ahead and I saved those for the end because that's something that in a chemistry lab that is pretty common to do, is to use what is known as litmus paper and test whether or not something is an acid or a base. Now, litmus paper is a it's kind of like it's a paper that is sensitive to acids and bases, obviously. Um, and it is going to be kind of your indicator. Hey, this is an acid, or hey, this is a base. Now, here's an example of what that looks like. Litmus paper is this is kind of it's kind of a weird looking image. Um, but this is on the left-hand side known as blue. Oh, that's not what I wanted. I want my textbooks. Blue litmus paper, and then we've also got red litmus paper. Your red litmus paper will turn blue in a base, and blue litmus paper turns red in an acid. Now, is this like a is this super red? No, it's kind of a pinkish red. But that's what the common terminology is. People describe that as a red piece of litmus paper. There's also a type of litmus paper known as neutral litmus paper, and that goes over an entire different range of colors, um, depending on how acidic or how basic something is. Now, here is an example or a video of an active metal in an acid. So this is magnesium, a magnesium strip in hydrochloric acid. You drop it in, and immediately it starts bubbling. And as it bubbles, it kind of breaks down and goes to the bottom. That magnesium, that solid magnesium, is breaking down. And just as a little bit of a preview, um, this magnesium strip is doing what's known as oxidizing, or it's getting oxidized. That's something that we'll talk about later on this week and early next week, but it's breaking down. It's reacting with that acid solution. Now we can proceed from there. So that's an example of an active metal and how it changes in the presence of HCl. Okay, so definitions for acids and bases. These are some definitions that, well, it can get kind of hairy because I know whenever I first took a chemistry class, we kind of had to know all of these different acids and these different definitions. There's an Arrhenius acid, or there's a Bronsted-Lowry acid. And the way that I want you to think about them is with these two definitions. An acid is something that donates a proton, and a base is something that accepts a proton. So, I could just say, like, to look at an example kind of chemical reaction, I would say, let's go with AH. Okay. AH plus H plus. This right here, that is what we commonly refer to as a proton. And from AH plus H plus, we would get AH. How many H's do we have in this compound over here? If we've added one and another, add to the chat how many um, hydrogens I've got on the right-hand side of my reaction there. So I got two. I also want to include a positive because it accepted the second one, and that second one had a positive charge, and this right here was neutral. So neutral plus positive equals positive. Now, where does this definition of an acid or a base, where do those things come into play in something like this? Well, what we want to do to look at, or what we want to look at there is we would want to say, all right, well, AH. AH goes to AH2. So AH accepted a proton. So this is a base. AH is the base. Now, if we were to look at something like this, I'm going to go, actually, not AH, I'm going to go with BH. And I'm going to write a chemical reaction. BH yields B minus plus H plus. So BH yields B minus and H plus. Well, in this case, BH is an acid because it donated a proton. It lost a proton to become B minus. So keep those kind of definitions in your head whenever you're thinking about an acid and a base. I think that it's best to come up with like an example to look at as opposed to just, memorizing this. It's good to start with this and say, okay, well, yes, an acid is a proton donor. So that's something that gives up a proton. A base is a proton acceptor. Got it. But be able to apply those. So, if you're sitting at home and you're like, I need a good forearm tattoo, this and this would be both some heavy hitters, some good forearm tattoo action there. With that said, if you elect to get a forearm tattoo based on what I've said in this class, I'm not responsible for any of the consequences. And I'm actually joking whenever I say you should get a forearm tattoo. I don't think that it's a good idea. For this, if you want to get one for any other reason, that's fine. I respect that. It's your decision, your body, your choice, and everything. But this, no, 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 not for. And that would be cheating. So if, however, you're now inspired, you're like, I love chemistry. That's awesome. And you want to get that forearm tattoo? Okay, I've spoken too much about forearm tattoos. But what I want you to do is know those definitions, but be able to apply those definitions. That's probably more important than anything else. Okay, now I'm going to clear my drawings and proceed. So reactions in water. So when we look at this, and here's kind of a follow-up to that, where I've added a little bit of complexity to it. We've got H2O and HCl. These two things react with one another. HCl becomes Cl minus. H2O becomes H3O plus. Okay, which one of these is the donor? Add this to the chat. Which one donates the proton? Is it HCl or H2O? And keep in mind, I'm describing things that are on the left-hand side. So which of these two? Is it H2O or HCl? That is the proton donor. That's donating the proton. So here what we've got is HCl. And what does it look like? So if we compare this to this, what's the difference? Well, it doesn't have the H. So HCl donated the H. It got rid of the H. H2O, by contrast, now is H3O plus. It accepted. So that would mean that this is the acid and this is the base. Now, one thing that I know people always struggle with this, and I always struggled with this, is I would look at it and I'd be like, okay, well, that's great going from left to right, but what if I read it from right to left? That would change everything, wouldn't it? Yes, it would. 100%. There's no doubt about that. So if we were to look at the reaction going in the opposite direction, does that change what everything is? Yes, it does. But don't get hung up on that. That's one thing that people have a tendency to get hung up on, where they're like, oh, but if I look at it backwards, I'm not asking you to look at it backwards. I'm giving you direction of read it from left to right. Okay. So there are all my drawings there. Now our pH scale ranges from 0 or roughly 1 to 14. So that basically any and every solution is going to have that range. This is always kind of weird because, typically you think about solutions like Coca-Cola or orange juice or an orange and oranges, orange juice, urine, pure water, blood, seawater. Okay, those are all going to fall along this range. Um, Everything can. If you got a steak and you blended it up, that steak is going to have a particular pH. Now, acidic solutions have a pH lower than 7, and basic solutions have a pH greater than 7. Solutions that have a pH of exactly 7 is what's known as a neutral pH. Now, everything about this is all kind of variable in terms of its magnitude. Some of these things are less acidic than others. For instance, HCl or gastric juices, the solution in your tummy is going to be more acidic than urine, is more acidic than tomato juice. It's more acidic also than, well, baking soda. Baking soda is more basic than soda. Now, a solution with a pH of 10 is, and this is our first top hat question for the day, and I don't have a lot of time on this, or I gave you a shortened time frame for this question. A solution with a pH of 10, is it acidic, basic, neutral, or is it toxic? Now, that reference is, of course, very outdated because that song's about 20 years old, but it's a Britney Spears song. If you've ever heard it, that's fine. Here we go. First top hat question. A pH of 10 is considered, and got a timer going on my watch. Is it acidic, basic, neutral? And I changed my answer options. I decided to not give you toxic as an option because it's not toxic. pH of 10. Best definition. About 15 seconds left. And of course, the consequences for getting this question wrong are pretty much nothing. Just want to see where everyone's head is with this. 3 seconds. Done. We got 21 responses. That's great. Absolutely. 17 of y'all got it correct. A pH of 10 is considered basic. Remember, under 7 is acidic, exactly 7 is neutral. Now, this question was not asking about relativity. This was asking, how would you define this singular solution? A pH of 10. You could, but we're not doing that in this question. You could say which of these, a pH of 10 is considered blank compared to a pH of 12. Well, you could say that it's more neutral, or it's even more acidic or less basic. Those are all good descriptors, and that is something that is done with different solutions. So basic is our correct answer. Good job, everyone. Next up is looking at calculating pH. So pH is equal to the negative log of hydrogen ion, or the concentration of hydrogen ions. As the hydrogen ion concentration increases, does the pH increase or decrease? Okay, so if our pH is, let's say, okay, these two things are inverse. So hydrogen ion concentration, as this goes up, that means a solution is more acidic. Okay, so what that means also is a thinking about it in terms of a question, which solution is more acidic? We've got solution A and solution B. Solution A, where the hydrogen ion concentration, those brackets there, that those indicate the molarity, is 0.1. Or B, hydrogen ion concentration, and this is 0.1 molar, 0.0001 molar. Which of these solutions is more acidic? And to answer that question, you're asking yourself, which one of them has the higher hydrogen ion concentration? Now, add to the chat, is it A or B that is more acidic? Which one of them has the higher hydrogen ion concentration? Essentially, which one of those numbers is larger? Morgan? Man, oh man, your calculator's messed up. Or your keyboard is, you put a question mark, and I know that you meant to put an exclamation mark. A is the correct answer because A has a concentration that is greater than B. So if it's helpful when you see a number like this versus this, change it and think about it in different units or maybe units that are more familiar. So A is our correct answer because 0.1 molar is more concentrated than 0.001 molar. Now, with that in mind, when you see a calculation like this, okay, what's the pH of this solution? Okay, in order to solve this sort of question, what you do is you take the hydrogen ion concentration and you type negative log on your calculator, and then you put in this number, 0.001. Is everyone ready for that? I think that the phone, you might have to switch the phone to a different function. Or if you do a Google, yeah, just type into Google or any web browser, negative log 0.001. Okay, so let's go. Top hat question. Is it 1, 3, -3, below 1? Now, as we answer this, I'm putting a timer on. Let's go ahead and process these answer options together. Okay, 1, maybe. 3, maybe. -3. What's a range of our pH scale? It's from 0 to 14. Can you have a solution with a negative pH? That's my question. I'm not going to answer that question because I know that the range is from 0, which is not a positive or a negative number, all the way up to 14, which is a positive value. Okay. Then just type in negative log 0.001. We got 20 seconds left on this one. After that, okay. Okay, what do we got? What do we got? I think we got 3. Booyah, you're absolutely right. Okay, so the -3, what I was trying to get at was negative, you can't have a negative pH. You can have a positive pH, and that positive pH will be anything greater than 0 all the way up to 14. So that kind of gave us, well, it could be below 1. Yeah, 0.0001, possible. 1 and 3, okay? Now, another way that people can do this, and this is the sort of question you'd see on an exam, is if I gave you a solution that was plus hydrogen ion concentration 0.00001. This is a little bit of a shortcut for you. Now, you're taking that number and you can put it in your calculator, negative log 0.00001. Okay, 4 zeros and then a 1. That log function, that's a log base 10. And essentially what this is going to ask you is how many places did you move the decimal? 1, 2, 3, 4, 5. Okay, let's look back at this. 1, 2, 3. Our pH is 3. If I gave you negative log and the hydrogen ion concentration was 0.00001, that means your pH is 3. So that can kind of save you some time on a question like that. And you will have a question like that on your exam. So anticipate that and be ready with that. I mean, that saves you a lot of time right there. Okay, now clear up my drawings. I don't think we have any more top hat questions, but we got a couple more slides. Let's see what we got. We've got 4 more slides. Okay, so measure pH with litmus paper. Here's your demo. Okay, so we already kind of looked at that. Our pH is less than 7. We got red paper. Our pH is greater than 7. We got blue paper because it's more basic. Now, here is our simulation. If we were to make a acid-base solution and use pH paper. So there's a special paper that is like all pH range. And if it gets, this is like it's called universal indicator solution or universal indicator paper. And when you put that into a neutral solution, it turns green. When you put it into an acidic solution, oh, my paper turned orange, magenta even. Whenever I add a base and I put it in there, it gets this like bluish, dark blue. So that's what this is trying to show. Now, let's go ahead and make a solution. And right now, I'm guessing our solution is neutral. It's pretty neutral. Well, it's a little acidic there. Let's go ahead and drop the concentration of our base of our acid. Oh, we're getting slightly more neutral. If we add or if we reduce the strength of our acid, or even more neutral. Now, what we're going to be doing over the course of Wednesday's lectures, we're going to be talking about acids and bases and their strengths. So here we have a very weak acid and we have a very small concentration of it. And what we get from that is we have a neutral solution. Okay, now, like I was saying, there are solutions that are more acidic than others and more basic than others. Sorry. Now, when it comes to kind of measuring pH of a solution, there are a couple of different ways that you can do it. And one is actually by using a red cabbage juice. So basically you get a red cabbage and you don't put a vice on it or anything like that, but you kind of squeeze that juice out and it's a really good indicator solution. It will change colors based on the acidity of the solution. So that's a pretty cool kind of at-home chemistry test you can do. Now, what we're going to do, we'll take a gander at this real quick. We've got a pH scale. Oh, I had it. It disappeared. Sorry about that, everyone. Here, if we were to look at the pH of like water from the tap, it should be a pH of about 7. Now, what that looks like on the micro level, well, we've got an equal concentration of proton donors of acids. Our acid would be H3O plus, and of a base known as HO or OH minus. If we were to adjust the concentration of either one of those, well, then we would see that our solution changes. So let's look at the pH of soda, or as they say in other parts of the world, pop or Coke. Well, that's going to have a pretty acidic pH of about 2.5. Now, if we were to change that solution to hand soap, big news, hand soap has a pH. It's not a solution like water is a solution, but it still has a pH that can be measured. It's a fairly basic pH. Now, that's one of the things that if you think about one of those properties that we described earlier of bases being kind of slippery. Well, hand soap is kind of slippery. Okay, well, I think that this is what I wanted to lead up to with respect to acids and bases. On Wednesday, we are going to be talking about strong acids and strong bases and kind of distinguishing between those, what make them different from one another. So if you're thinking right now, what should I do with respect to, what we covered today? There's a couple of different things. One, you should know the definitions of an acid and a base. And you should be able to look at some example kind of equations. What's your hydrogen or what's your proton donor? What's a proton acceptor look like? Those would be really helpful for understanding the sorts of questions that you would have on this. And then with respect to the, log calculation, make sure that you have a calculator that you can use to do a log calculation, because that's going to be very powerful and very helpful when you're doing your um, exams. Now, with that in mind, how many questions am I going to give you about calculating what the pH of a solution is? One, maybe two. And I already wanted you to think about like that shorthand, that quick way to do that calculation. I think that's a good start, being able to convert from 0.001 to what the pH is. That would be a valuable thing to do. I'm going to be posting some quizzes tonight that will be due on Sunday at 11 p.m. Some covering today's stuff, Wednesdays and Friday stuff. You'll have 2 attempts, 15 minutes, and they're open. Other than that, though, I want to say thank you guys very much for coming to class. I really appreciate it. And I will see you guys on Wednesday. Um, if you have any questions between now and then, please don't hesitate to send me an email, ask me a question, and I'll get back to you as soon as I can. Um, but thank you very much for coming. I hope you have a good day and a good Tuesday. Okay, I got a private message about top hat questions from Friday. Yes, I will post those, and I'm gonna give yeah, I'm gonna post those up. So all right. Thank you guys.